In the last video, we introduced the summation formula. Quick ways for summing 1 plus 2 all the way through n, or for 1 squared plus 2 squared through n squared, or the same for cubed. Now we want to look at a few examples of how to use them. So let's consider, for example, you're asked to find the sum from I equals 5 to 10 of I. So what does this mean? Recall this just means you're summing up 5 plus 6 all the way up to 10. Starting at 5, going to 10. Well, your first concern should be, here I have a sum that does not begin at 1. And in my formula, I always begin at 1. But we have a way of fixing that. We can think about the sum, 5 through 10, as secretly being the sum of 1 plus 2 all the way up to 10, minus the sum of 1 plus 2 all the way up to 4. So summing up 5 through 10 is summing up everything from 10, and then subtracting off the 1, 2, 3, and 4, leaving you just the things 5 and bigger. But now that I've written it like this is the same as just finding the sum from I equals 1 to 10 minus the sum from I equals 1 to 4 of I. And now these are the right form that we can use a formula. The sum from 1 to 10, n is 10. So we get 10 times, that's n, times n plus 1, that's 11, divided by 2. Minus the sum from 1 to 4, that's just going to be, n is 4 now, so 4 times n plus 1 times 5 divided by 2. And then simplifying, this is 5 times 11, which is 55, minus 2 times 5, which is 10, so we get a sum of 45. Great. The summation formula gives us a way of solving things even when it doesn't begin by 1, by thinking of it as a subtraction of two different formula. Notice that since it was just I, we used the first formula. If it had been I squared or I cubed, we would have used the second or the third formula. Let's look at one more example. Suppose you're asked to calculate what is the sum of I cubed minus 3I squared plus 4, where I goes from 1 to whatever number you want. Let me just say we go to n. Later on, if you want to plug some number in from n equals 5, we can do that at the end. But let's try and think, how can we solve a problem like this? So this might seem elusive because we don't have a formula for something like this. We have a formula for I cubed, we have a formula for I squared, but we don't have something for minus 3 times I squared, right? So how might we do something like this? Here's the observation. What this is encoding is this is saying this is the sum, plug in 1 cubed minus 3 times 1 squared plus 4, plus plug in 2, because I is going 1, 2, 3 up to n, plus 2 cubed minus 3 times 2 squared plus 4, plus, and keep going until you plug in n, all the way up to n cubed. We're plugging in n now for the I, minus 3 times n squared plus 4. Now, the trick is we're going to remember that addition and subtraction we can move around. So we can group all of these 1 cube, 2 cube, 3 cube pieces, n cube pieces together to have, so just grouping all of these terms, we get 1 cubed plus 2 cubed all the way up to n cubed. Okay, track with me, we're going somewhere here. Next, we'll group together all of these next terms to get something of the form minus 3 times 1 squared, minus 3 times 2 squared. I can just pull out the minus 3. So I can say plus 2 squared, plus all the way through n squared. because if I distribute the minus 3, I get minus 3, 1 squared, minus 3, 2 squared, through minus 3, n squared. And then finally, I just have a whole bunch of copies of 4 laying around. A whole bunch of copies of 4. Plus 4 plus 4, just a whole bunch of copies of 4. If I put this back into my summation notation, this is the same as saying the sum of I cubed, where I goes from 1 to n, minus a 3 times the sum of I squared from I equals 1 to n, plus the sum of 4 from I equals 1 to n. I'm just adding up 4 n times. It's first copy of 4, second copy of 4, up through the nth copy of 4. Now, here when I was trying to show you how this works, I went through all these steps. In practice, you can skip from here to the bottom, where all you're doing is you can think you're distributing the summation. You're pulling out you're breaking it up from I cubed minus 3i squared to a summation of I cubes minus 3 times the summation of I squareds, plus the summation of 4. So you can think of it as distributing the summation throughout. Okay, what's the advantage of doing this? When we break this up in this way, we now have pieces that we have formula for. The I cubed formula is just n squared times n plus 1 squared divided by 4, minus 3 times the I squared formula, which is n times n plus 1 times 2n plus 1 all over 6. Plus, well, we don't have a formula for this one, but let's think about it a little bit. What is 4 plus 4 plus 4 plus 4 where there are n copies of 4? Well, that would just be 4 times n. In general, whenever this is a constant, it's just that constant times n. Okay, if you want to, you could simplify this more, but I'm not going to worry about that. The point is I was able to get an explicit formula. If I wanted to sum from I equals 1 to 10, just plug in 10 for your n. If you want to sum from 1 to 100, just plug in 100 for your n. Whatever it is, you can do that. But now we see that summing this up is the same as just plugging in your n and calculating what it comes out to be.